In this last series of videos, we're going to start talking about using carbonyl containing compounds like aldehydes and ketones and even esters, but in a new way that we haven't talked about thus far. And all the reactions that we've looked at up to this point, the carbon is the electrophile and a nucleophile is attacking this carbon. What we're going to look at in this series of videos is actually turning this carbon into a nucleophile by deprotonation. This is called the alpha carbon. So one way that we can sort of summarize all the chemistry that we're going to learn in these videos is alpha carbon chemistry. It turns out that the hydrogens next to the carbon of a carbon-oxygen double bond called the alpha carbon, those hydrogens on that alpha carbon are quite acidic, at least for CH bonds, and we can do interesting chemistry by deprotonating that alpha carbon. Excuse me. So in this video, we're going to talk about generation of those kinds of nucleophiles at the alpha carbon. Those are called enolates, and also the related compounds, which are called enols, and then how we generate those compounds under either equilibrating or non-equilibrating conditions. So the alpha carbon, as I mentioned, is the one right next door to the carbon of the carbon-oxygen double bond. So you have the carbon here of your carbon-oxygen double bond. One carbon away is the alpha carbon. 2 carbons away is the beta carbon. 3 carbons away is the gamma carbon. This particular ketone has 2 alpha carbons and has 4 hydrogens that are available for deprotonation at those alpha positions. And being able to identify alpha carbons and CH bonds that are on alpha carbons is going to be really important for understanding the reactions that we're going to be talking about in this series of videos. So what's an enol? We've talked about this but very briefly in class. So it turns out that all carbonyl containing compounds exist in a rapid equilibrium between the ketone tautomer and the enol tautomer. So these are 2 different isomers, right? These are not resonance structures. So we're not drawing a resonance arrow here. These are actually, there's an equilibrium that exists between 2 different isomers of a ketone. One is called the ketone tautomer, one's called the enol tautomer, and this equilibrium is called tautomerization. So as we've seen in the past, if an enol is formed like from hydration of an alkyne, that can rapidly tautomerize to form the ketone, and this can happen under acidic or basic conditions, as we're going to see. Before we talk about the mechanism for forming enol tautomers, the first thing that you want to keep in mind is this is one of the first examples of an equilibrium that we're going to look at where the starting material is actually almost exclusively favored. So 99.99% of our mixture, or more than that, is going to exist in the ketone form, and only a very, very small fraction is going to exist in the enol form. Okay, so let's say that we have cyclohexanone, and we said that under acidic conditions we can form the enol tautomer. What would be the mechanism for that reaction? Well, the first reaction, let's say we have acidic water. Just like in all the other reactions that we've looked at, the first step is going to be protonation of our carbon-oxygen double bond. And in the other mechanisms, what we've seen is that a nucleophile attacks this carbon. Formation of an enol, you want to think about it similarly to like an E1 reaction. Keep in mind that this has a resonance structure, right, that places a positive charge on that carbon. And remember back a long time ago when we were talking about nucleophilic substitution versus elimination, right? If you have this carbocation, it could undergo an SN1 reaction, so a nucleophile can attack that carbon, or it can undergo an E1 reaction, which would involve loss of a hydrogen next to it at the alpha position, right? So we have an alpha carbon here, we have an alpha carbon here, and we said those hydrogens are acidic that are alpha to that carbon-oxygen double bond. So instead of drawing water as a nucleophile, water can also act like a base, or whatever solvent that we choose can act like a base, and it can accept this proton, and now we generate an enol. Every single one of these steps is reversible, right? And if we look at this step, right, if we look at this, the stability of our starting material versus stability of our product, here we have a very strong carbon-oxygen double bond, but here we have a weaker carbon-carbon double bond. So actually the reason why the ketone tautomer is favored much more than the enol tautomer is the fact that the enol tautomer is less stable than the ketone tautomer. What about under basic conditions? How would we draw the formation of an enol under basic conditions? Well, we start with the same ketone. But now, remember, under basic conditions, right, hydroxide and all the mechanisms that we've looked at previously, hydroxide can act like both a base and a nucleophile, but in the previous reactions, hydroxide immediately attacks this carbon as a base. Instead, the first step is going to be deprotonation of the alpha carbon, right, to generate what is called an enolate ion. So generally speaking, right, hydroxide will not deprotonate CH bonds. So what's going on here? Why does this work? Well, the reason is because this is a resonance stabilized carbanion, right? We can draw a resonance structure here where that negative charge is shared between the carbon and the oxygen. And that oxygen can accept a proton from water or whatever the solvent is to regenerate a hydroxide ion and our enol tautomer. So in the formation of an enol tautomer under basic conditions, we have an enolate intermediate, and these are two resonance structures of the enolate, which is the negatively charged intermediate that's generated when we deprotonate this alpha carbon, or the hydrogen that is present on the alpha carbon. In this particular mechanism, we protonated the enolate to form the enol. Okay, so speaking of enolate ions, the rest of almost all the reactions that we're going to talk about in this series of videos are going to focus on the tremendous how useful reaction at the enolate position can be, or the alpha carbon. So for the rest of this video, we're going to talk about different bases that you can use to deprotonate this alpha position to generate enolate ions. And as you can see, right, we can imagine this would be really useful, right, because we have a negative charge on carbon, and so we've formed a nucleophilic source of carbon where we can turn this into a nucleophile and use it with reactions of electrophiles to make useful compounds. So this is called the enolate ion when we deprotonate a ketone or an aldehyde at this alpha position. Okay, what's interesting about enolates is that even though we have two resonance structures of the enolate, we can draw it as a negative charge on oxygen, or we can draw it as that same negative charge on carbon. Remember, the reality is that the negative charge is shared between oxygen and carbon, and for thermodynamic reasons that I just kind of mentioned here, right, alkylation of carbon, so if this negative charge on carbon reacts with an electrophile, we form a new carbon electrophile bond, and we retain a carbon-oxygen double bond, which is more stable than a carbon-carbon double bond. Imagine if the oxygen reacted with the electrophile, we would end up with a carbon-carbon double bond. It wouldn't be as stable. So whether you draw this resonance structure or this resonance structure, you always want to show reaction on carbon to give a new carbon electrophile bond in your product. Okay, so what bases can we use to make enolate ions? One type of base is hydroxide or alkoxide ions. So if you have ethoxide, or if you have methoxide, or if you have hydroxide, right, the pKa of alcohols and water is around 16 to 18, whereas the pKa of an enolate is somewhere again between around 14 to 18. So what you'll see is an equilibrium, right? So if we look at the strength of this acid versus the strength of this acid, they're roughly equal. So what we get is an equilibrium here where there's a measurable concentration of the ketone or aldehyde form, and there's a measurable concentration of the enolate form. And we're going to see examples of reactions where it's really important to have a concentration of both the aldehyde and the enolate, right? Sometimes you want to have both of these things present in the reaction, and under those types of reaction conditions you want an equilibrium, so you're going to choose an alkoxide like ethoxide or methoxide or hydroxide ion as your base, so you can establish this equilibrium that has a measurable concentration of both species. Whereas other times you don't want an equilibrium. You might want to quantitatively deprotonate your aldehyde or your ketone. In that case, you could use a reagent like sodium hydride. Hydride is a very strong base which can deprotonate this alpha position, and this is an irreversible equilibrium. Hydrogen gas bubbles out of the reaction and we get only the enolate ion out of this reaction. And similarly, if you use a really strong base like LDA, lithium diisopropylamide, this negative charge on nitrogen is much more unstable than this negative charge on carbon because it's resonance stabilized. Or if you look at the strength of this acid, this is a much stronger acid than this one. So the equilibrium shifts all the way to the product side. So now we have only enolate. We don't have any aldehyde left, and we don't have any aldehyde left in either one of these reactions. So if you want to exclusively form your enolate, if you want to do this under non-equilibrating conditions, use sodium hydride or LDA instead of the previous conditions that we talked about. What's interesting though is as you continue to stabilize that negative charge, right? If you have a dicarbonyl, right? Now we have a resonance structure that can be stabilized in this direction or in this direction. So now the pK of this hydrogen is much more acidic, right? Because the conjugate base is more stable. So even ethoxide or methoxide or hydroxide will give us non-equilibrating conditions, exclusive formation of the enolate. So we don't have any ketone or aldehyde form. We've converted it all to the enolate if we have a dicarbonyl. Okay, to summarize this video, you always want to look for the alpha carbon, because the alpha carbon is the carbon that's next to your carbon-oxygen double bond, and that's going to have an acidic CH bond, and that proton can be removed to generate an enolate ion. And as we're going to see in the future videos, the chemistry of the enolate ion is very important for creating biological molecules. How do we generate enolates? One way we can do it is under equilibrating conditions, sodium hydroxide, methoxide, or ethoxide most commonly. Or we can do it under non-equilibrating conditions. And again, what we're going to see in the future videos is in some cases you want equilibrating conditions and in some cases you don't.